Hello and welcome to this course Machinery Fault Diagnosis and Signal Processing. Today we will see one case study in sugar industry. Now sugar industry is a process industry where the sugar cane is converted into sugar crystals. First the sugar cane is converted into molasses, and from the molasses it converts into sugar crystals. Molasses is basically a thick syrup of sugar cane juice, and this molasses has to be chemically processed to convert it into white sugar crystals. Now, in the sugar industry, there are various processes are carried out, and to carry out those processes, various processing equipments are required. Some processes such as cutting, crushing, evaporation, crystallization, separation of sugar crystals from molasses, etc., etc. Uh, and to carry out these processes, various processing equipments are required. These processing equipments are interlinked with each other. That means failure of any of the processing equipment would hamper the entire production. That is why they are interlinked. One process is depending upon the other process. Unless and until one process completes, next process cannot be carried out. These processing equipments are interlinked with each other, and failure of any of the processing equipment would result in production loss or production stoppage. Now, out of these processing equipments, some are extremely critical. Some equipments like can be bypassed, so they are less critical. But some equipments which you cannot bypass it, or which you cannot maintain it in a standby. So such equipments are categorized as extremely critical components. Those critical equipments are leveler, cutter, fiberizer, shredder, ID fan, SA fan. SA fan is basically a secondary fans. Then steam turbines, mill motors, centrifugal pumps, etc., etc. Um, to carry out condition monitoring in any of the processing equipment, you have to follow certain fixed steps. Uh, and what are those fixed steps? The first step is periodic vibration measurement of the machine under consideration to judge its present condition and presence of fault in the machine. First, you need to check the status of the machine, and first you need to check whether the fault is present in the machine or not. If the fault is not present in the machine, then there is absolutely no need to carry out a condition monitoring. The first step is to check the present status of the machine. The second step is frequency domain and phase analysis to diagnose the exact location of the fault. In the first step, if we identify that there is a presence of fault in the machine, then the second step would be to identify the exact location of the fault. And to identify the exact location of the fault, we need to process the signal, vibration signal, into frequency domain plot. And frequency domain plot analysis would give the indication of the probable location of the fault. We can determine the exact location of the fault by analyzing the frequency domain plot. Then once you identify the presence of fault and the location of the fault, next thing is to find out the severity of the fault, how severe the fault is, how much time it will take to completely break down the component, what is the remaining useful life of a component. So all these things can be identified by determining the severity of the fault. The fourth step is to take the corrective action against the fault. So if you take corrective action, if the fault is at early stage, then you can prolong the life of a component by large period. And if the severity of the fault is such that very less amount of time is required, uh, then by taking some corrective actions, you can actually prolong the life of a component. Then fifth one is measurement of overall vibration levels to check the effect of corrective action. So whether the corrective action is effective enough or not. To check it, we again have to take the vibration readings and actually come to a conclusion that the fault has come down to allowable level. So these are some of the fixed steps which you need to follow to carry out the condition monitoring of any of the mechanical component. Uh, these are the some characteristic frequency of machine faults. You should have the knowledge of characteristic frequencies, because the knowledge of these characteristic frequencies will actually help you in detecting the exact location of the fault. uh, the first column indicates the types of fault. The first is unbalance. So when the rotor is unbalanced, imbalance actually happens in the rotor kind of a component. So when there is an unbalance in the rotor, then you will get the highest amplitudes of vibration in the radial direction. Uh, the frequency is 1 into RPM. The probable causes is erosion, corrosion, deposition on the rotor. The example of unbalanced rotor can be an ID fans in the power plants. The ID fans are placed just before the chimney. The ID fans extracts the flue gases from the boilers and take it to the chimney, and from the chimney it releases into the atmosphere. Now, when the ID fans receives the flue gases, the suspended particles in the flue gases get deposited on the rotor blades, and because of that deposition, uh, the balance of the rotor get disturbed, and since the ID fans are running at extremely high RPM, this small unbalance becomes very catastrophic, and the vibration may cause the damage to the ID fans. So this is one example of unbalance. The second type of fault is parallel misalignment or looseness. You will get the highest amplitudes of vibration in horizontal and vertical directions or in radial directions. The location is 2 into RPM. Uh, these faults are basically because of the installation error. Then angular misalignment. In angular misalignment, you will get the highest amplitude of vibrations in axial direction at 1 into RPM frequency. The cause of the failure is because of the installation error. Then the next type of fault is anti-frictional bearing faults. Uh, Unsteady vibration, highest amplitudes of vibration acceleration at characteristic frequencies. Uh, the reason of anti-frictional bearing faults may be because of the lubrication or contamination in the lubrication, shocks, etc., etc. Then the last type of fault is gear fault. In the gear fault, you will get the highest vibrations at gear mesh frequency, and the gear fault may be because of the lubrication, contamination in the lubrication, shocks, erosion, corrosion of the gears. This particular case study is carried out in the sugar industry, and one of the critical component of the sugar industry is Fiberizer. Fiberizer is basically a component which removes the fibers from the sugar cane. It is a very heavy equipment. In the picture you can see that the rotor of the Fiberizer weighs up to 10 to 15 tons. This rotor of the Fiberizer is directly coupled to a motor. The motor is connected to variable frequency drive, wherein you can change the RPM of the motor, but it has been observed that most of the time these Fiberizers are running at its full RPM, that is 750 RPM. The motor size is 500 HP, so you can imagine the amount of power it requires to separate the fibers from the sugar cane. So it's extremely heavy motor running at 750 RPM. The vibration readings are taken at the bearing positions. The Fiberizer rotor is supported at two bearings. The one indicates the non-drive end bearing and the two indicates the drive end bearing. First thing is to check the vibration status of the Fiberizer. First we'll check whether the presence of fault is there in the Fiberizer or not, and for that we have taken the vibration readings at non-drive end bearing and drive end bearing. We have taken the readings in horizontal, vertical and axial directions. Uh, we have measured the vibration in terms of displacement and velocity. So if we see the velocity levels of non-drive end bearing in horizontal, vertical and axial direction, then in horizontal direction it shows 23 mm per second, that in vertical direction it is 17, and in axial direction there were no readings were taken because there were no sufficient space for installing the accelerometer. That is why the axial readings in case of non-drive end bearing is not available. Then the same procedure is carried out for drive end bearing, and readings are taken at horizontal, vertical and axial. So out of the non-drive end bearing and drive end bearing, we can see that the highest vibrations is in non-drive end bearing horizontal direction, and it shows 23 mm per second. So first we will check whether these vibrations, the highest vibration is within the allowable limit or not, because that only give the indication of presence of fault in the Fiberizer. So for that we will refer the ISO 2372 standards for machine vibrations. So the ISO 2372 standards give the allowable velocity vibrations for class 1, class 2, class 3 and class 4 machines. These machines are categorized into class 1, class 2, class 3 and class 4 depending upon the driving motor. If the driving motor is up to 20 HP, then it is categorized as class 1. If it is from 20 to 100 HP, then it is categorized as class 2. If the machine is driven by more than 100 HP with rigidly mounted on foundations which are stiff in the direction of vibration measurement, is class 3. And machines with more than 100 HP motor but mounted on foundations which are flexible in the direction of vibration measurement, then it is categorized as class 4. So as far as Fiberizer is concerned, it comes in the class 3. And if we check the ISO 2372 machine vibration standards, then this 23 mm per second vibrations for class 3 comes out to be in the not acceptable region. So that indicates that there is a presence of fault in the Fiberizer. So our first step of fault diagnosis has been completed, and we have identified the presence of fault in the Fiberizer. Now next step is to find out the exact location of the fault, and to identify the exact location of the fault we need to process the signal in frequency domain. So this is the frequency plot of non-drive end bearing in horizontal direction. So here you can see that the prominent peak is at 2 into RPM frequency. So if you refer the characteristic frequency chart, then 2 into RPM peak is because of the parallel misalignment and looseness. Okay, so uh, for a prominent peak at 2 into RPM indicates two possibilities, either parallel misalignment or looseness in the bearing or foundation. So first it is decided to check the misalignment between the motor shaft and Fiberizer shaft. So a dial gauge is installed on the coupling flanges of the motor and Fiberizer to check any shaft misalignment. It was found that the shaft misalignment was within the tolerance limit. The misalignment is checked by using a dial gauge and it was installed on the flanges, and the readings were taken at 0 degree, 90 degree, 180 degree, 270 degree, and it was observed that the shafts are uh, properly aligned within the tolerance limits. Then it is decided to check the looseness in the foundation of the Fiberizer motor, and when we check, then all the foundation bolts were properly fixed. So then it is decided to check the looseness in non-drive and bearing block of the Fiberizer. On opening the bearing block, the clearance was observed between the shaft surface and the sleeve of the spherical roller bearing. The clearance was measured using feeler gauge and found to be 0.3 mm. So it is concluded that the increased vibration levels were because of the looseness in non-drive end bearing. So we check the clearance between the sleeve and the rolling element by using a feeler gauge. Feeler gauge is basically a bunch of thin plates or thin strips of different thicknesses, and when we check the clearance was observed in the load zone as 0.3 mm. So every bearing manufacturing company gives the allowable clearance limit in the bearing, and when we saw the allowable uh, limit of the bearing SKF 2220 CN self-aligned type, then it was observed that the maximum allowable clearance is 0.09 mm, whereas in our case it was 0.3 mm. So it was not like it was more than the allowable clearance. So the looseness was because of the clearance in the bearing, increased clearance in the bearing. So to remove the clearance, it was decided to tighten the lock nut of the sleeve, but clearance was there even after the full tightening of the lock nut. The sleeve was not grabbing the shaft surface properly. This indicates that the shaft is worn out at the sleeve seat, and so also the sleeve. The sleeve was worn out, so the entire shaft along with the Fiberizer rotor was taken to the heavy duty industry for making its sleeve seat proper. First, the worn out surfaces of the shaft was filled with welding deposition on it, and then it was turned to the required dimensions. And then again the bearing was installed, and uh, then we again checked the vibration levels. After the correction, the vibrations were reduced considerably at 2 into RPM. So that indicates the effect of corrective action. This is how this particular fault has been eradicated, removed from the Fiberizer. So this is the case study of Fiberizer, that is of bearing looseness. So thank you very much. Thanks.